Hello friends and welcome to average classes. Okay, so now we have come to your fluid kinematics part 2. Interesting. That is your description of your fluid motion, description of the motion. So imagine we must play cricket, like we are playing cricket, we are playing football, we are playing billiards. So I have to three examples. We have to three examples. One is your it's a cricket ground. Consider you are in a cricket ground. Okay. Now your Mahendra Singh Dhoni is batting. Okay, so when Mahendra Singh Dhoni is batting and you are seeing where he is hitting sixes. So first he hit a six here. Okay, next he hit here. Then again he hit a six here. Then one more six here. So Dhoni is hitting sixes and this is your ball. This is your ball. So every time he hitting sixes, from where the reference point is? So reference point is where he is batting. Reference point is where he is batting. So from that you are tracking what? You are tracking the ball. Where did the ball go? So first the ball went in the right side direction. Then the ball came to the left side direction. Okay, like your up side, leg side. Okay, long on, long off. He has hit sixes. So what you have done is you have tracked. Okay, this is the way the ball has traveled. The ball has traveled like this. We see these things in our graphics, isn't it? The cricket graphics, they show which direction he has hit the six and how did it has go. So keep that in your mind. Okay, now come to the football field. So here is your reference. Okay, here is your football reference. So they started. So this ball traveled like here, then traveled here, then traveled somewhere here, then traveled here. From here, goal. Okay, so here also, we know how the ball has traveled before it has entered the goal post. Okay, or reached its destination. That's reached the goal. Good. That means we can track, the ball, the movement of the ball. Again from a reference. Where is the reference? Here is your reference. Midpoint is the reference. Okay. Now come to a billiard. Okay, this table. This here also what we are doing? Okay, you have just hit somewhere and one ball hit some other ball. One came here, other came here, and one suppose fell down here. So in each of the cases of this ball, you know their particular velocity. Let us say this is XA, the position XB, position XC, velocity VA, velocity VB, velocity VC. So in these examples, whatever I have given you, we can actually predict which way they will go. Which way they will go. So we have predicted which way they will go. Then what we can know? We will know how much energy or momentum they can exchange along with each other. So accurately, what? Sir, accurately we can predict that where they will go. Where the ball or anything, in this case cricket ball, football and your billiard ball, they will go. Okay, and also we can calculate the sir, amount of energy or moment they will transfer or exchange. They will transfer or exchange. That means what we are doing here? Sir, we are keeping track of individual what? Keeping a track of individual position and velocity vector. We are keeping a track of individual position and velocity vector. This is the reference point. Reference point is also known as their identity. Okay, that is the identity being here is the crease of your cricket ground. From there only he is hitting six. So I am knowing at what point what is the position of the ball and what is the direction of the ball, what speed he has hit. So I know the magnitude of the speed, I know the direction of the speed, which gives me the velocity, and I know with the position also. Okay, same is the case of your football, same is the case of your billiard also. That means I can keep a track of position and velocity vectors. If the same thing you'll apply to a fluid which is flowing. If the same thing is applied to a flowing fluid, that means you are keeping a track of the position and velocity vector of fluid particles. Such a method, we call it as what? Such a method is known as your Lagrangian. Such a method is known as your Lagrangian method of description of the motion. Lagrangian method. So Lagrangian, he was the Italian scientist. Okay, let me just erase this. He's an Italian scientist. Okay, so who has given a method, and he told, okay, we have to, in order to predict the motion of a fluid, we need to go for the position and velocity vector of individual fluid particles. Okay, Lagrangian. Okay, Italian scientist. He was an Italian mathematician priorly. Around how much? 1783 to 1813. Okay, full name Joseph Louis Lagrange. Joseph Louis Lagrange. He has told, okay, we have to, for each and individual fluid particle, you should know the velocity and position vector. In order to understand it little better, let us think about, this is a river. Okay, and okay, mountain just I have drawn. सबसे पहला काम सुंदर diagram. Okay, now we have a tree. From this tree one leaf fell. Now what you are doing? You are tracking the way the one individual leaf has traveled. So the leaf has been traveling like this. So every point I am calculating, this leaf went like this, then the leaf went like this, then it came somewhere here. So in each case, what I am doing, I am tracking the position and velocity of individual leaf kind of thing. Then such a method is known as your Lagrangian method. Okay? But sir, is it easy? We can accurately know where they will go and all. But sir, is it easy if you are applying to a fluid? It's definitely not easy. Okay, it's not easy to track down the position and velocity vector of each and individual particle. Okay, see, in solid you have two distinct solids, so you can find their position, velocity vector, whatever you want. Okay, and you can predict how much energy is being transferred between them. But what happens in a fluid? First of all, it's very difficult to identify a fluid particle when it is moving around. Okay, when it is moving around, it's very difficult to identify. Second point of view, if you think macroscopic point of view, your fluid is a continuum. That's what we have to kind of assumption. Continuum means they are very closely, they are very tightly packed. There is no gap between them. So how you are going to describe, or how you are going to predict how much energy being transferred between them? Okay, how much energy or momentum they have exchanged between them? If you think microscopic point of view, a fluid particle, a parcel of fluid, that is its identity, a parcel of fluid is made of billions of fluid molecules which are continuously zoom banging around with each other. Okay, so that means even if you will take your fastest and smartest computer, it will be very difficult to identify their flow properties. Okay, that is to track their velocity and position. Very difficult, even if one subset of that fluid parcel if you will take. So okay, so keeping these things in your mind, it's becoming very difficult. So sir, that means we do not have any application of this. We do have an application. For example, here, like I told you, your fluid contaminant study, like where they are going and all, you have to find. It's a tedious job, but you have to do it. Okay, see this pandemic. We have decided 6 feet duri. Okay, maintain 6 feet, and how much distance your particles can travel with mask, without mask. Okay, one person with mask, how many other person it can impact, and all these all studies, this fluid particle or contaminant study, this you can do with the help of your Lagrangian model. Okay, second thing, when your space shuttle is your spacecraft is re-entering to the Earth's upper atmosphere, where there is a rarefield gas dynamics, there Lagrangian study becomes again much more predominant. So we do have its applications. Okay, it's not like we do not have its application. Now we'll write it. Okay, then we'll go to the solution of Lagrangian model, the other model. Okay, understood? Good. So Lagrangian method, we'll note down this. individual fluid particle is selected and is observed throughout its course of motion. Okay, through the space as it is moving through the space. We have took an example of a leaf here. Okay, now it requires to track the position and velocity of each individual fluid parcel. That is the particle with what we have decided. Okay, a parcel, small element. Okay, that's a part of fixed identity. Its identity is the reference itself. Okay, that means every time we are telling the property, velocity, acceleration, something, so every time we have to take the reference or that is identity. So it is a what you call not that much handy for mathematical calculation and all. Okay, and why it is difficult, so much difficult? Basically we are deciding 4 reasons. Number 1, how will you identify a fluid particle as they move around? Okay, and as we know, a fluid is a continuously deformable body. It's a continuously deformable body fluid. So how you are going to go for the fluid particle? Now you can go, but I am telling these are difficult. Okay, now in microscopic point of view, fluid is a continuum. Because fluid is a continuum, that means very continuously space, there is no void, anything is present. So how the interaction you will find? Which interactions are? Energy and momentum interaction. Okay, between individual particles. Now if you go to microscopic point of view, fluid is composed of billions of molecules that are continuously banging into one another. That means in order to track and to find the position and velocity of that, even a subset of this small portion, by a fastest or a smartest computer also is going to be a very tedious job. That's why Lagrangian method becomes very difficult for us to do. Okay, and its application we are going to write in but it has some applications, okay, where we cannot use Eulerian method. So for that I will write in the next slide. Okay, pause the video, note it down. The application point of view, like I told, tracking of passive scalars in a flow to model contaminant transport. Like I just now in corona case, you have sneezed and those fluid particles. So individual particles we need to count, okay, and we need to track. Okay, then rare field gas dynamics, letters are little small. Okay, I will take care of that. Next time I will write little bigger. So the rare field gas dynamics, okay, calculation concerning the re-entry of space into the Earth's atmosphere. As the space enters into the atmosphere, the concept of continuum is not valid there anymore. So easily we can go for your Lagrangian model to calculate. Okay, next, development of visualization and measure of system-based particle tracking technique. Now see this. You have seen now some sci-fi movies, James Bond movie or G.I. Joe kind of a movie. Okay, you will find they will use some thermal sensor or some thermal goggle which will give the heat signature. What do you think? How they are developing those heat signature? By the particle tracking technique. By the particle tracking technique. See, that's the beauty of this fluid mechanics. See, what happens is when your air surrounding your body is hot, okay, so it will become lighter. It will become lighter means it will go up. So natural convection current will set up. That only it will capture. So in those cases, Lagrangian model we are using for describing the motion of fluid. Okay, note it down. Next we are going to study the Eulerian model. Okay. Other method of describing your motion of fluid is your Eulerian method. Leonhard Euler, a Swiss mathematician. He is the best mathematician. As per me, he is the best mathematician ever born. Okay, so he is your Leonhard Euler. What he did is, now instead of tracking a single fluid particle, what he did is he asked Bablu. Bablu is my friend. Okay, Bablu. So what he has done, he has asked Bablu to stand here. So Bablu stood here. Okay, Bablu. They told, so Bablu can see up to this range. Okay, so what he asked is, when the fluid particle is traveling from this point to this point, you tell me its velocity, you tell me it's the pressure, you tell me the acceleration. Okay, then he asked Pappu. Pappu is one more friend of mine. Okay, then he asked Pappu to stand here, and he asked Pappu, so Pappu can see up to this range. Okay, so he told Pappu, okay, when the leaf which fell from here, remember our previous example? Okay, so when the leaf is traveling from this point you from this to here, you tell me what is its pressure, what is its velocity, what is its acceleration. That means instead of tracking the fluid along its total way, what we chose is, we chose our point of interest. Okay, this is my point. At this point, when the fluid is traveling, what is its velocity, at what velocity is traveling, at what acceleration he is having, okay, or what is the pressure, what is density. These are the flow characteristics defined at the point. The flow characteristics has been defined at a point. That point is our interest. Okay, why sir, why would I do that? See, I'll tell you some examples. Now you have wing of your aeroplane, okay, and the wing, below the wing I have kept a probe, a velocity probe. So when fluid is like, your plane is moving and it is cutting through this cutting through the air, so at that point the velocity probe will tell me what is the velocity of the wind. Okay, or let us say wind tunnel. In your wind tunnel, what happens? In your wind tunnel, your aerofoil or your plane is present, but the probes are connected at particular points. So at that points we are measuring what is the velocity, what is the pressure, what is the acceleration. We are not following the entire flow. Okay, so it gives us an upper hand for mathematical calculations and everything. I need not to track down the entire fluid motion. Instead, what is my point of interest? There I will have some probes and I will measure the velocity, acceleration, pressure, whatever you like. Okay, I'll give one more example. Okay, let me continue so that you will write this. So this is what at any point, here it is about point. At any point in the space occupied by the fluid is selected, that is our point of interest, and we made the observations and take notice of or write what are the properties that is changing or it is constant. So properties means your velocity, here we are talking about acceleration, here we are talking about pressure. So what we write here, I'll just write a finite volume called flow domain. So this is the finite volume called flow domain or the control volume we have selected. This is my control volume, CV, control volume. So that means the fluid can come in and out of this control volume, in and out. So that means what? Mass change as well as energy change is taking place. So in thermodynamics term, it is an open system. In a thermodynamic term, this is the open system. Whereas your Lagrangian method is only mass change. That is the analogous to thermodynamic term closed system. Okay, analogous to closed system. This is analogous to open system. Define the flows in or out. We define field variable. What are the field variables, sir? Sir, pressure is a field variable, which is scalar field variable. Pressure is a scalar field variable. Take velocity. Velocity is a vector field variable. Okay. Take acceleration. Acceleration is also a vector field variable. So we define here control volume. Okay. We define field variables at particular locations. So these locations we define the field variables. What are the field variables? Sir, field variables are function of space and time. This is, remember, that's why the fluid kinematics, this velocity, acceleration, everything, which are the field variables, they are function of space and time. Means here your pressure, which is a scalar field variable, this is also a function of space and time. Means I can write pressure P of x, y, z, t. X, y, z is my space, t is the time. So similarly, velocity, this v of x, y, z, t. So velocity is a which? It's a vector. P, pressure is a scalar. So it's a vector field variable of space and time, x, y, z and t. Similarly, acceleration, a vector field variable of space and time. So continuously we will be discussing about x, y, z, t, that is space and time, because by default we are taking the field variables. Within the control volume we will find it. Okay, super, fantastic. Means what is the velocity, acceleration and pressure when the fluid came inside the control volume and came out of the control volume. Okay. Now here we don't really care about the individual fluid particle, rather we are interested in the pressure, velocity or acceleration, whichever fluid particle happens to be our interest. For example, in a wind tunnel, my interest is the velocity. So I'll find the velocity vector field. Okay, in some other application I need a pressure measurement, so my pressure field variable will be pressure. So this total field variable, that is pressure field variable, scalar field variable and the vector field variable collectively is known as your flow field. Is collectively known as flow field. So field variable you understood, which is a function of space and time. It may be pressure, it may be velocity, it may be acceleration. You understood flow field. Flow field means that collectively this field variable is only known as your flow field. Okay, and control volume you understood. It is an imaginary volume where the fluid can come in and come out. Okay, that means it's analogous to open system. Analogous to open system. So Eulerian method actually made my work quite easy. Okay, just I need to fix my point of interest and whenever a fluid is passing through that, I have to find out what is the velocity, pressure, acceleration at that point. That's all. Okay, so this method is more convenient for fluid mechanics application, for example in a wind tunnel or experimental methods. Okay, this you understood, right? So this is your Eulerian method. Pause the video, note it down fast. Now in conclusion for your Lagrangian method and Eulerian method, remember Lagrangian method, the kinetic behavior, that is your pressure, velocity, acceleration, density, etc. Pressure and velocity and acceleration are studied for any fluid particle with respect to time. Okay, it's for a fluid particle, whereas Eulerian method is at a point. The kinetic behavior is studied at a point in a flow field. This represents analogous to the closed system. This represents analog to the open system. Okay, this is Eulerian method or Eulerian method is widely acceptable and widely used. Okay, good. For this and flow identity, that is the reference point is necessary. For here reference point is necessary, not necessary. Fixed point we are deciding. Because we already know the fixed points, the things becomes quite easy for us. We can take as number of fixed points as we want. Okay? Got it? Very good. Now, in order to make it little more easier, you are traveling. This is you. You are sitting. Okay? And you are moving your vehicle. You are driving your vehicle. Your vehicle has a GPS. Okay? Now, you are driving at 60 km per hour, 80 km per hour. It's a highway. You found, highway is completely empty. So you started the acceleration and you 180 km per hour you are now going. Okay, so this entire your vehicles, how the velocity you started 60, then you went to 70. Next time at t equal to, let us say t equal to t naught, this is your 40 km per hour. Then t is equal to t1, you are around 60 km per hour. Then next time interval you have gone to 140, 160, 180 km per hour. See, so your vehicles, I have only targeted one vehicle, that is your vehicle. Your vehicle's fluid velocity I am continuously monitoring 40, 60, 80, 100, 140, 150, 180. Correct. So that's through the space. That's why I told you your vehicle has a GPS. So continuously throughout every location, at all location of your vehicle, I know your velocity. Okay, that is your Lagrangian method. Okay, now you are going in national highway. You know there is a speed probe. Correct. There are some instrument speed probe that you cannot speed limit. You cannot cross 150 km per hour or 100 km per hour. So that's why to test that they have some speed probes in your national highways. Okay, and that national highway you have crossed. Zoom. So while you have crossed, at what speed you have crossed? They don't care whether you have before you are crossing at 40, traveling at 40 km per hour or 80 km per hour or 100 km per hour. They don't care that. While crossing that speed probe, zoom, at what velocity or what speed you have crossed. Suppose you have crossed the speed limit, then a nicely challan will come to your address. Okay, because of overspeeding, that you have crossed the speed limit. So that probe which is fixed there and you want to know the velocity of that method is what the Eulerian method. I hope now this Eulerian method is and Lagrangian method, the difference between them is clear to you. Okay, so thanks for watching. Okay, clap yourself if you have watched till this end, and any doubts please write in the comment section and let me know. Have a great day ahead, and if you haven't subscribed to the channel yet, please do subscribe. Thank you.